We're going to do the Toricelli's tank or draining tank lab for this fluid dynamic little station here. So what you need for this lab is some sort of pop bottle. Actually, soda bottle, not pop. Get that right, all right? Some sort of soda bottle. Empty it out. It doesn't have to be 2 liter, but 2 liter works a little bit better than the 1 liter. What you do is you take this soda bottle, empty it out, and then what you do is you're going to cut a small little hole near the bottom of the bottle. So right there. Now I made mine a circular hole. I want to have you guys make it a square hole because it's easier to find the surface area of a square because it's just space times height. It says to cut a 1 centimeter by 1 centimeter square on the bottom. Now, you can estimate the best you can, but all of you should have some sort of tape measure. Now, you can get a tape measure that actually has the metric centimeters on it, or you can just assume that a little bit less than ½ an inch is a centimeter. So you want to cut a little hole very carefully in the bottle right there. It doesn't have to be at the very bottom, just some amount. So the next thing you're going to do with your bottle is you're going to make a line, like a mark, a horizontal line somewhere in your bottle. If you want to cut off the top and fill it to that mark, that's fine too. I just made a line. And then I'm going to measure the height above that line. So I'm going to take my tape measure and measure from the top of that hole to that line. So from the top of this hole to wherever that line is, that's going to be my h in centimeters. So I'm going to write that down. There's a little data table here. I'm going to write that value down. How many centimeters is that? I'm going to just make up a number here. 15.5 centimeters. Now if you have inches, make sure you convert to centimeters. Then the next thing it's going to have you do is find the diameter of the container. So what you do is you measure the actual diameter of the container itself. From here to there. You measure that diameter. I'll make up a number, maybe it's 6.6 centimeters. These are totally made up numbers, but there's the diameter. Then the idea is to find the surface area. What's the surface area? Imagine this is the outer edge of the container. What's the surface area? Big A, we'll call that. This is the big surface area. What's the surface area of that? And the way you get that is it's pi times the radius squared. So we're going to cut that in half. So it'll be pi times diameter over 2 quantity squared, because that's what the radius is. So whatever you got for that value, that's going to help you find the surface area of the bottle, in, at least the cross-sectional surface area in square centimeters. Now finally, the small surface area, assuming you did your measurements and cutting right, it's just be a small hole that's 1 centimeter by 1 centimeter. So the surface area of that is 1 square centimeter. Assuming it's right. If it's not, make sure that you account for that in the data table. All right, now what we're going to try to figure out in this lab experiment is a couple things. How fast is the water going to be coming out of the tank that's draining? How long, and also how long will it take that tank to drain? So we're going to use something called Toricelli's Theorem to answer that question. Now Toricelli's Theorem is this. He stated that fluids, like water for example, will follow the laws of conservation of energy, which is probably the most important topic in physics. And here's how it applies. Let's say you had a tank filled with water, like this. That water has potential energy. This water at the top, it wants to fall down. So the water at the very top, it wants to get to a lower height. So the water starts with potential energy, mgh. That potential energy, as the water starts to fall, will end up becoming kinetic energy. So eventually all of that potential energy will turn into kinetic energy. So it says that potential energy equals kinetic energy. Now, it doesn't matter what the mass of the water is, what the viscosity of the water is, whatever that is, the flow, the velocity of the water coming out of this tank at the bottom depends only on one thing, the height, and I guess the acceleration of gravity. So you notice the mass cancels out. If I were to solve for v, I get v is equal to the square root of 2 times g times h. So the initial velocity of the water in the fluid, the initial velocity will equal 2gh. So it's dependent on this. Remember, h has to be measured in meters, so you have to convert to meters. So Let's see what that looks like. So here, I filled this tank up with water, and I have that hole there, if you remember. I'm going to release my finger on the hole, and we're going to see water come out. I'm actually going to show you a couple different angles of what happens. So here we go. So as you notice, the water starts coming out pretty fast. But as time goes on, that draining starts to slow down. You notice that the stream is actually getting less and less as time goes on. And this is because the height's changing. And as the height lowers, the velocity is going to become less and less, until the final velocity of this becomes 0 once it reaches the very minimum height. So the initial velocity is given by square root of 2gh. The final velocity is given by 0 because the h is 0. So the average velocity of the fluid is going to equal the average of those two values, the average between your initial velocity and your final velocity. So essentially you can find the average by just cutting your initial velocity in half. So to figure out how much time it's actually going to take to actually get the water or fluid to flow out of the tank, we're going to have to talk about something called flow rate. Now, flow rate is basically the amount of fluid that travels through a certain region of space in a given amount of time. And you've probably heard of some of this before. There's actually two different ways to measure flow rate. There's volume flow rate and there's mass flow rate. They're essentially the same thing. You can convert from one to the other, just like miles per hour to meters per second. They're measuring the same thing. There's two different ways of looking at the same thing. So here's some common ways that volume flow rate is measured or like talked about. There's cubic meters per second, like how many cubic meters of water are flowing in a river per second. There's centimeters cubed per second. There's milliliters per second. There's gallons per second, like how much fuel does a certain engine use per second is usually measured in gallons per second. Liters per second, same thing. So these are all volumes per second. Now, similar to that, we can convert that using a conversion to talk about mass flow rate. And for those, we usually use kilograms per second, but there's also grams per second or pounds per second as well, using pounds as a form of mass measurement. So we can use the ideas of these to figure out how much time it actually is going to take that tank to actually drain. So there's actually a couple different ways to calculate volume and mass flow rates. So I think the most easy way to calculate it is, let's start with the bottom on mass flow rate. To figure out mass flow rate, you just find the total amount of mass that flowed in a given amount of time. So let's say that I had that tank, and in 15 seconds, it released 30 kilograms of water. So the mass flow rate for that would be given by 30 divided by 15, which is 2 kilograms per second. And that would be the average mass flow rate. It's not going to always be at the same rate, but the average mass flow rate is going to be 2 kilograms per second. Okay? I can do the same thing for volume. Let's say it was like 2 liters. I go over 30 liters of water in 15 seconds. Well, then I can know that that's going to be 2 liters of water per second. That's how fast it can go. But the cool thing is with volume flow rate, there's actually another way to calculate it, and that's actually the way we're going to calculate it in the lab. Is to use, and this is a symbol for flow rate, by the way. It's the psi. That's how you can calculate flow rate, or it's a symbol for it. But it's given by the area of the hole. Think back to the little opening that we cut in that container, times the average velocity of the fluid. So let's say the average velocity of the fluid, not the maximum velocity, but the average velocity. Let's say we found it to be 7 meters per second. And the area of the hole was 1 square centimeter. Well, we have a little bit of an issue here because these aren't in the right units. But I can make them in the correct unit by either converting this to square meters or converting this to centimeters per second. I think it's actually a little easier to convert this to centimeters per second because 7 meters per second is just 700 centimeters per second. Easy conversion, all right? So the average flow rate of this would be, well, 700, and then the units would be square centimeters times centimeters is cubic centimeters per second. And look at that, that's a volume flow rate in cubic meter per second, or cubic centimeters per second. Then all you have to do, if you want to get the mass flow rate, is use something called density. Density is the conversion between mass and volume. So essentially, here's the symbol for density, is equal to mass divided by volume. So the cool thing about water has a specific density. The density of water is 1 centimeter cubed per gram. So 1 gram per cubic centimeter. It's also equal to 1 kilogram per 1 liter. Or 1,000 kilograms per cubic meter. And those are exact numbers. We built density and volumes and stuff around water. So 1 gram per cubic centimeter, 1 kilogram per liter, or 1,000 kilograms per cubic meter are the densities for water, assuming that water's at room temperature. So we can use that conversion to say, all right, we're at 700 centimeters per second, centimeters cubed per second for the volume, and I want to find out how many grams of water are flowing per second. Well, I know that 1 gram of water is equal to 1 cubic centimeter, so it's a 1-to-1 ratio. So there's 700 grams of water flowing out of that tank every second. All right, totally made up numbers, but hey, if the tank was 10 meters tall, that's what would happen. It'd be pretty fast. All right, so let's do a quick example of a question like this. I have a 10 meter tall, by 10 meter long, by 10 meter deep tank of water filled to the top. So it's 10 by 10 by 10 meters. And at the very bottom, I have a 1 square meter hole, pretty big hole, all right? And the question is, how long will it take this tank to drain, all right? So there's a couple steps here. What I'll need to do first is figure out the velocity of the water coming out of the tank. And I can use Toricelli's Theorem to figure that out. Conservation of energy, 2GH, the H that I will put in would be 10 meters. We'll assume that the height of the water is 10 meters above the hole. So that gives me a velocity of 14 meters per second. That's my initial velocity. The average velocity is just going to be half of that because the average of the initial and the final, which is 0, is just the middle. So the average velocity, so V average, will equal 7 meters per second. Awesome. Now, next step is to figure out the flow rate. What is the flow rate of water coming out of that? So if I want to find the volume flow rate, I can just use area times velocity. The area of the hole is going to equal 1 square meter. And the velocity is going to equal 7 meters per second. So meters squared, meters, that gives me a value of cubic meters. So I get a value of 7 cubic meters per second. That's the volume flow rate. Now if I wanted to figure out the mass flow rate, let's say how many kilograms of water are flowing per second, then I would just use unit analysis. I know that the density of water is 1,000, so I could use, all right, well, 1 cubic meter is 1,000 kilograms. So I end up getting 7,000 kilograms, because just cancels out, per second. That would be the mass flow rate. But I don't really need that. I just want to show you how to convert that. So given the 7 cubic meters per second, that's my average flow rate. If I want to figure out the time, how much time it takes, well, I need to figure out if it's going 7 cubic meters per second, I just need to know how many cubic meters there are in this. So I can use the other equation for volume flow rate and know that it's going to equal the volume divided by the time. And if I know that this is 7, well then I just need to find the volume of this tank. Now for you guys, you have a cylinder tank, so it's going to be the area of the circle times the height. Oh, okay. For me, it's just 10 times 10 times 10, which is 1,000 cubic meters. So solving for that, I can figure out the time it would take for this tank to theoretically drain. So, that's what you're going to do in this lab. You're essentially going to build your own tank with your own hole and then allow it to drain and figure out how much time it's going to take using unit analysis and Toricelli's theorem. So using Toricelli's theorem, flow rate, and conversions, unit analysis essentially, you can figure out how long should your tank take in order for it to drain. And then you'll test it out. So, if you have any questions, feel free to ask. Otherwise, best of luck to you. Happy draining.